Good morning, students. So, electronic material technology. So, the applications of nano material. Okay. So, today's topic, we start with some simple discussion. Yes. What after ULSI? Okay. What is meant by ULSI? Start with the basics. Okay. So, in IC technology, SSI, LSI, MSI, and VLSI and ULSI. What is SSI? Small scale integration, then MSI medium scale integration, LSI large scale integration, and VLSI very large scale integration. Yes. So in last semester you studied about the VLSI. Yes. Next, what is ULSI? Already we discussed ultra large scale of integration. In SSI technology, normally it contains 1 to 12 gates. Okay, or number of transistors means up to 10 transistors we can tell. Then MSI up to 12 to 30 gates, okay, logic gates. Then in case of LSI 300 gates, and up to VLSI 10,000 gates. There is nothing but 10,000 up to 1 lakh transistors, okay, per chip. In case of ULSI, beyond 1 lakh transistors is possible in case of ultra large scale of integration. My question is this the end? Whether it is the end in technology, or what kind of technology we are having after ULSI? Yes. Okay. Yes. What is the basic rule we are following? Is technology mantra. What is technology mantra for VLSI? Moore's law. Yes, good. Moore's law. What Moore's law states that? So the number of transistors count is double every 2 years. Or generally we are telling every 18 months. Both are correct. Okay. So the figure shows the technology overview. It starts from the microprocessor 4004 up to, yes, now what here i5, i7, Intel i7 processor, and go on. Okay, so up to 10 billion transistors. Okay, in 4004, just see the diagram, 2300 transistors per chip in case of 4004 microprocessor. Okay, but now in case of your i5 processor, it has almost 1.3 billions of transistors per chip. Just see. But what about the size? What about the size? That is the question. Okay, so this is considered as a technology mantra, is nothing but your Moore's law. Okay, yes. So just to see the diagram, what about the vacuum tubes you studied in VLSI? Just recall. Okay, so the size of the devices is reduced. Okay, even though we increase the number of transistors per chip. Okay, yes, that is the technology view. Yes. So the today's topics is moletronics. That is molecular electronics. Okay, molecule plus electronics. We are getting a moletronics. It is a branch of electronics in which individual molecules perform in same function as molecule electronics devices, such as your diode and transistors. It is similar to your transistor. Okay, so how the transistor is work, how the rectifier is work, how the diode is work, the same way here the molecular electronics is also work. Here the electronics is built with the help of the molecules. Molecular electronics is the study and application of molecular building blocks for the fabrication of electronic components. Okay, so these are the scientists. They start from the invention. Okay, from the molecule, how they work. Okay, yes. Now, so in molecular electronics, okay, what is the applications, how it works, okay, what is the basic building blocks, what are the approaches we have to go through in molecular electronics, we will discuss one by one. Okay, okay. Generally, it is also an interesting approach to significantly reduce the fabrication cost compared with the previous method, as well as the energetic cost of computation compared to usual semiconductor technologies. Okay, already you studied the basic, okay, how the IC is fabricated and how it is meant by CMOS technology, what is by CMOS, already we studied. Okay, it is a very different one compared with that one. The important one is the fabrication cost compared with the previous conventional technologies, okay, is high, but in case of molecular electronics it is very much less. So we are following two methods. One is the top down approach and bottom up approach. Conventional electronic devices are traditionally made from bulk materials. Bulk materials have inherent limits, that is for growing increasingly demanding and costly. Thus, the idea was born the components would, instead of building up atom by atom in chemistry lab. Okay, so atom by atom in a chemistry lab we are developing, it is nothing but bottom up approach. Okay, it is just opposite to the top down approach. Okay, so in figure shows top down approach and bottom up approach. In top down we starts from the bulk material, then powdered material and goes to the nanoparticles. But in case of your bottom up approach, we starts from the atom by atom and go to the nanoparticles. So that is the comparison between top down and bottom down approach. Okay, please go through that one. Yes, so the very much important one is nothing but the production cost. Okay, so what about the production cost? Here the very much high, here the production cost is low. Okay,